Question 21 says a source emitting a sound of frequency f0 starts moving towards an observer at a large distance with a uniform acceleration a. The frequency heard by the observer corresponding to the wave emitted just after the source starts is given by the expression p f0 square v by p f0 v minus 5a, where v is the speed of sound in the medium. The value of p is. So here the situation is something like this. Let's say the source starts from here, and here is the observer at a large distance, and let's say the source has started moving at time t equal to 0. Let's say this distance was d. So if at time t equal to 0 source has started moving, and let's also assume that at t equal to 0 itself the source emits a pulse, and so we find what is the time at which this pulse will reach O, and what is the time that the next pulse will reach O, and the difference of these two will give us the frequency corresponding to its initial position, and from that frequency we can find the time period. So at t equal to 0 pulse is emitted and the source also starts moving, so the time at which it will reach is t1, and the value of t1 will simply be equal to the distance. We have assumed that the initial distance between the source and the observer was d. The wave is moving with speed v, so this time will be d divided by v, right? The motion of source has got nothing to do with this time, so this is initial time. Now the next pulse will be emitted after time 1 by f0. Okay, so let's say the source has moved this distance, and well, this distance we can find by applying kinematics, and this distance we know can be given as half a and the time that it has got. Okay, so the time it has got is in fact 1 by f0 into square. This is the expression for this distance. So this distance then becomes d minus half a 1 by f0 square. So time t2 will be, the pulse is emitted at time 1 by f0 after the first pulse, so that time will be there, plus the time it takes for this pulse to reach the observer, and that time again can be given by the distance, which is d minus now a by 2 f0 square divided by v. This is t2. We now find t2 minus t1, and we have to find the frequency, so we find t2 minus t1, and the inverse of t2 minus t1 will give us the frequency. So the value of t2 minus t1 is 1 by f0, and d by v term will cancel, so it's minus now a by 2 f0 square into v. Well, let's simplify this further. So this is 2 f0 square v in the LCM, and in the numerator we are going to get 2 f0 v minus a. So the frequency, well, frequency heard by the observer corresponding to the waves emitted just after the source starts will be inverse of this. So that frequency, let's simply call it f, is equal to 1 by t2 minus t1, and this in turn is 2 f0 square v divided by 2 f0 v minus a. Well, if we put a factor, because here the coefficient of a is 5, so we multiply both numerator and denominator by 5, and in that case the frequency we shall find is equal to 10 f0 square v divided by 10 f0 v minus 5a, which means the value of p is 10. So for question 21 the answer is 10. Let's go to the next question now. Question 22 says a small sonic source emitting sound of frequency 1088 Hz is rotated in a circle of radius 100 by pi centimeter at a constant angular speed of 5 revolutions per second. A detector is located in the plane of the circle outside it. The difference in the maximum and the minimum frequency recorded by the detector in hertz is, and the speed of sound in air is given as 330 meter per second. The question is based on again Doppler effect, and first of all we find the speed of the sonic source, and that speed v is omega into r. What is the value of omega? Well, it says that angular speed is 5 revolutions per second, so that means 5 into 2 pi radian per second is the angular speed, and this multiplied by 100 by pi centimeter, that is the speed in centimeter per second. We find that it is equal to 1000 centimeter per second, and that is in fact 10 meter per second. So this is the speed of the source. Now the maximum frequency will be heard or will be recorded when this source is moving, in fact approaching the observer, right? It's something like this. Let's say the source is moving along this circle, and here is the observer. So at this instant, when the source is going in the anti-clockwise sense, maximum frequency will be heard, and when it's going away along the line joining the two, then minimum frequency will be heard. So the expression for maximum frequency, F max, let's call it, will be the frequency emitted, which is 1088 Hertz, and it's a case of source approaching the observer being stationary. It will be the speed of sound, which is 330 divided by 330 minus 10, or 320. This in Hertz will be the F max, and the F minimum, it will be 1088, and 330 divided by, in this case it will be 330 plus 10, or 340 Hertz. So these are the maximum and the minimum frequencies. Well, simplifying, we find that the maximum frequency is coming out to be equal to 1122 Hertz. It's just a matter of simplifying this. And minimum frequency, well, is coming out to be 1056 Hertz. Again, simplifying this expression, and the difference of the two is 1122 minus 1056, which is 44 plus 22, that means 66 Hertz. So the difference F minus F minimum is coming out to be 66 Hertz. So that is question 22. Let's go to the next question now. Question 23 says, consider the situation shown in the figure. The wire of mass m gram oscillates in its fundamental mode and sets the air column in the tube in its third harmonic. If the tension in the wire is 260.1 Newton and the speed of sound in air is 340 meter per second, the value of 10 m is. Well, it's a case of resonance, and the string is also oscillating and the air column is also oscillating. The air column is oscillating in its third harmonic. That means we can consider that the length of air column, because it's oscillating in third harmonic, so 1 meter is equal to 3 times lambda by 4, where lambda is the wavelength of the sound wave. So if 3 lambda by 4 is 1 meter, so 3 lambda by 4 is 1 meter, this means lambda itself is 4 by 3 meter, and this will give us the frequency of the sound wave, because we can find the frequency simply by dividing the speed by wavelength. The speed is given as 340, so it's 340 divided by 4 by 3, and if I divide this, this is 85 into 3, so this is 255 Hertz. That is the frequency of the sound wave, and that must also be the frequency of the string. Now we have frequency as, that means 255 Hertz. As far as the string is concerned, is that the string of course is oscillating in its fundamental mode, so that is equal to speed of the transverse wave divided by 2 times the length, and speed of transverse wave is under root t by mu. So t in fact is given to us, and that is 260.1. Mass per unit length will be m into 10 to the power minus 3 kg, and the length is 40 centimeters, so it is 0.4. and this in fact is V, and we divide this by 2 times 0.4, and this frequency we have found is 255 Hertz. So now squaring both sides we can find the value of M, and if we square both sides what we have is this. Of course this radical sign covers this M2. So what we have now is 260.1 into 0.4 into 10 to the power 3 divided by M, in fact is equal to 255 into 0.8, and we have to square this. Now we have the expression. It's simply a matter of finding the value of M, and the value of M comes out to be equal to 2.5, and that means 10M is 25. So that means for question 23 answer is 25. Let's now go to the next problem. Question 24 says 2 coherent narrow slits emitting sound of wavelength lambda in the same phase are placed parallel to each other at a small separation of lambda by 2. The sound is detected by moving a detector on the screen at a distance capital D equal to 100 root 3 meter, where capital D is much larger than lambda, from the slit S1. See figure. D is the distance in meter from O, such that path difference at P equals half the path difference at O. The value of small d by capital D is. So we simply have to look at the path difference, and since lambda is very small compared to capital D, we can consider that the path difference, of course, which is S1P minus S2P, can be given as, let me draw a separate figure here. This is say S1 and this is S2, and let's say the figure goes something like this. So we draw a perpendicular, and let's say this P is at a large distance. So if this angle we take as theta, this is S1 and this is P, let's call it A, then we can consider that at point P the path difference between the two sources would be S1A. We have just drawn a perpendicular from S2 to A, and these two lines can be taken almost as parallel. So we have to find S1A, and we can see that the value of S1A in fact is given to be half of S1S2. So which means S1S2 in fact is lambda by 2 and S1A is lambda by 4. So we have in this right angle triangle cos theta is equal to 1 by 2, and that means we can take theta as pi by 3. Now to find distance of point O from, or rather distance of point P from O, taking this angle as pi by 3 and using tan pi by 3 as root 3, we know its value. This in fact is equal to small d by capital D, and well, then small d by 10 is equal to d root 3 by 10. Let's now put the value of capital D, which is 100 root 3 into root 3 by 10 is simply equal to 30 meter. So that means answer to question 24 would be 30. Let's now go to the next problem. Let's now go to the final problem of this test. Question 25 says the equation of a standing wave produced on a string fixed at both ends is y equal to 0.2 centimeter sine pi by 25 centimeter inverse x sine 400 pi second inverse t, where one end of the string is at x equal to 0 and the other end at x equal to L. The smallest possible value of L in centimeter is. Well, what we see here is that the equation of the standing wave is given to us, and by comparing it, we can compare it with y equal to a sine kx sine omega t, and by that comparison k we find is equal to pi by 25 centimeter inverse. So this is, and we know that the value of k is also 2 pi by lambda, which means that the lambda is here, well, 50 centimeter, and the minimum length of the string should be lambda by 2 if it vibrates in its fundamental mode with only one loop. In that case, this length L must be lambda by 2, and that will be the smallest length. So that means the smallest possible value of L in centimeter is 25. So answer to question 25 is 25 itself. Well, with that we have come to the end of the solution. I hope you found the solutions helpful and useful. Wish you all the very best. See you again. Take care and bye.